Okay, so we're all here. Kiran is not here. Is Kiran attending today? Does anyone know? Can you hear me?
Yes, sir.
Okay. So should we wait a minute for Kiran? Okay, let me start then. Maybe he'll join later. So, okay, so let's see. Right. So we were talking about the hyperbolic n space Hn, right? And we saw that well, Hn has constant curvature -1. So sectional curvature of all two planes is -1. And for any two plane in the tangent space at any point, if I take the exponential of that two plane, then this is a totally geodesic copy of H2 in Hn, right? Okay. So tangent to any two plane, there is a totally geodesic copy of H2 passing through it, which you get by exponentiating that two plane. So is this okay?
Yes.
Right. And remember what totally geodesic meant. So there were two equivalent ways of saying this. So one is that every geodesic in the copy of H2 is also a geodesic of Hn. And the other way is that we define this bilinear map at each point called the second fundamental form, right? So the second fundamental form was basically the difference of the connection of Hn with the connection of H2, right? So it was the connection of H2 is the tangential part of the connection of Hn. That's what we saw for any isometric embedding. And so the difference of the two connections is the normal part, right, of the connection. So totally geodesic means the second fundamental form, which is the normal part of the connection, that vanishes, right? So in other words, the connection applied to vectors in to vector fields in H2, the connection of H2 applied to a pair of vector fields of H2 is the same as the connection of Hn applied to those vector fields. Is that clear? Right?
Yes.
Okay, fine. So now we're going to go towards the proof of Alexandrov's theorem that if X is a complete simply connected Riemannian manifold of sectional curvature less than or equal to -1 at all two planes, then X is a cat -1 space, right? So we've talked about cat -1 spaces. So these will give a class of examples of cat -1 spaces. namely simply connected complete manifolds with sectional curvature less than or equal to -1. Okay, so these will have variable negative curvature in general, right? The curvature is not a constant, the sectional curvature. Whereas for Hn, the sectional curvature was constant, equal to -1. So, okay. So, the key to this proof of Alexandrov's theorem is a study of Jacobi fields in Hn and Jacobi fields in the manifold X. Okay, so first we need this lemma that if I take a point P in Hn and U is a tangent vector, a unit tangent vector at P to Hn, and V is a vector in U perp, then if I take gamma to be the geodesic with initial condition U, so that means gamma 0 is P and gamma prime 0 is U, and I take J to be the unique Jacobi field along gamma with initial conditions J0 equal to 0 and J prime 0 equal to V. Okay. Then I can calculate the norm of this Jacobi field explicitly. It is equal to mod JR, where JR is the unique solution of the differential equation J double prime minus J equal to 0 with initial conditions J0 equal to 0 and little j prime 0 equal to norm V, which is equal to R. Okay. So maybe I'll draw you a picture for this and we'll see the proof is not difficult. So okay, so we're in Hn and I'm taking a geodesic in the direct gamma in the direction of a tangent vector U at P. And then I'm taking a vector perpendicular to U. So this is V. And then I'm taking a Jacobi field like this. Okay, so with J0 equal to 0 and J prime 0 equal to V. So this J comes through a one parameter family of geodesics. You can take them to be so gamma S of T. You could take this to be XP of T of U plus SV, right? V element of U perp in TPHN. Okay. And your Jacobi field you can get by differentiating this. So JT is del del S at S equal to 0 of gamma S of T, right? Okay, so then J0 is 0. And as we've seen before, J prime 0 is V. Is this clear?
Yes.
Yeah, we've done this calculation a few times before, right? You remember this? Yes?
Yes.
Okay. All right. So, so what happens? How do we calculate the norm of this Jacobi field? So what I can do is my P is lying in a copy of H2 inside Hn, a totally geodesic copy, right? Okay, so this is my Hn, and this is my totally geodesic copy of H2. And my curves gamma S, they also belong to this copy of H2, right? Okay, this H2 is what? H2 is XP of sigma, where sigma is the span of UV, right? Is this clear? Yes?
Yes.
Yes,
Okay.
sir.
Okay, so this means that when I differentiate the gamma S's, that means that my J will be tangent to H2, right? So JT will belong to the tangent space at gamma T to H2, which is inside the tangent space at gamma T to Hn. Okay, so now let me take N of T to be a unit normal. So this is H2, the tangent space is two-dimensional. So, okay, so maybe, so if this is gamma T, let me take N of T to be a unit normal vector. Okay, so N of T is in the tangent space to gamma T of H2, such that N vector is perpendicular to gamma prime and norm N vector is 1. Okay, so this is a unit normal vector along gamma. All right. Yes. So then my J, remember J will be J belongs to the space of perpendicular vector fields along gamma, right? J will be perpendicular to gamma prime at every point. Yes?
Yes.
That's
Yes.
right. Because J0 is perpendicular to U and J prime 0 is perpendicular to U. That gives us exactly the 2n minus 2 dimensional space of perpendicular Jacobi fields, right? So J is a
Sir,
perpendicular Jacobi field. So therefore J will be, since J is tangent to H2 and it's perpendicular to gamma prime, so then J is equal to F times N for some function N, right? For some function F. Yes, question?
Yes. So NT that I am choosing, I need to choose it smoothly, right?
Sure, yeah.
There are two options always. I mean,
Sure,
plus
sure.
and
There's just
minus.
two, right? There's just two, right? There's just two. Okay. Once I insist that NT is continuous, then there's it's uniquely determined, right?
Yes. Yes. Yes.
It just continuity will imply that it's uniquely determined, and then that it's actually. So actually, how can I get this NT? I take
You
a
just
unit.
parallel transport it, right? Along
Exactly,
the.
exactly, 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 exactly. So I can take NT to be
At gamma 0, I just take one.
PT of some N0. Okay.
Hmm.
All right. So this
Yes.
is yeah. So well, so the thing is, you want it to be tangent to H2. So I mean, this would be the parallel transport of H2. Okay. All right.
But
Yes.
totally geodesic implies that the
Exactly. Yeah. So
parallel
well,
transport will.
right. You have to be a bit careful. So what you
Hmm.
say is that the NT, it's so how do I say this? So I mean, the covariant derivative with respect to H2 of NT, this is, well, okay, so the covariant derivative with respect to Hn, let me look at, of NT. What is this? This is equal to the covariant derivative with respect to H2 of NT plus the second fundamental form applied to gamma prime and N, right? Is this clear?
Yes. Yes.
Right? This is
Right.
by definition of the second fundamental form,
Exactly. Yeah.
right? So the second fundamental is form is 0, and the covariant derivative in H2 is 0. So this is 0. So therefore NT is parallel along gamma. Okay.
Okay.
So N is parallel along gamma. Okay. So thus J double prime is equal to F double prime N, right? Because N is parallel. So when I differentiate J, I won't get any derivatives of N. I'll only get derivatives of F, right? Is that clear?
Yes, sir.
Okay. So now we use the Jacobi equation. So I know that 0 is equal to J double prime plus R gamma prime J gamma prime. Okay. So 0 is equal to, therefore, this J double prime is F double prime N plus R, and J is Fn. So I'll get an F coming out. F R gamma prime N gamma prime. And now I want to use that the sectional curvature is constant equal to -1. So I take inner product of this with N. Okay. So the first term becomes just F double prime. And the second term becomes what? It becomes inner product of R F times inner product of R gamma prime N gamma prime N. And this is equal to, by definition, the sectional curvature, right? At gamma T of the two plane spanned by
Sigma.
yeah, so gamma T and N, gamma prime and N into mod gamma prime wedge N squared, and gamma prime and n are perpendicular unit vectors. So gamma prime wedge n squared is just 1, and this is -1. So this becomes f double prime minus f. Okay. So therefore, J satisfies the differential, F satisfies the differential equation, f double prime minus f equal to 0. Okay. And what is f prime 0? So, J prime 0 is equal to f prime 0 n 0. Right? So I take norms on both sides. So therefore I get that norm V, this is equal to V. Okay. So I get that norm V is equal to mod f prime 0. Right? Is this clear? N0 is a unit vector, so this vanishes when I take mod, right? When I take norms on both sides. Is this okay?
Yes.
Yes,
Right,
sir.
so that proves the proposition, right? So norm J is equal to mod f. Okay, is equal to mod JR. Actually, what is JR? What is the solution of this equation with initial condition R? F0 equal to 0 and f prime 0 equal to R. What is this? JR. What is JR actually? Come on, this is a simple differential equation. What is the solution of this differential equation? With initial conditions, JR of 0 equal to 0, JR prime 0 equal to R. What is the solution? Come on, this is class 12 calculus. You should be able to do this.
So the general solution is C1 e to t plus C2 e to t minus t, and then we need to
Yes.
put
Right. So do that. Yes.
the
please.
initial conditions are set what? Can you repeat?
Yeah, the initial conditions are what? JR0 is 0, right?
And JR prime 0 equals to V.
Equals to R. V
R,
is a
R.
vector.
Right.
R is norm V. So what is the solution?
R by 2 e to the t minus R by 2 e to the minus t.
What?
Or maybe
Say that again. Yeah, say it again. Say it again.
R by 2 times e to the t minus
Yeah.
R by 2 e to the minus t.
Yeah. So what is that?
Oh, achha. R by 2.
R into what? That
Yes.
function has a name, right?
Right. Sine hyperbolic or cos hyperbolic or something. Yeah.
It's sin HT, right?
Right.
It's sin HT. It's sin HT. Okay. If you're doing any hyperbolic geometry, you should know your sin H and cos H at least, right? The basic properties. These functions will come up all the time, sin H, cos H. So actually, what does this lemma tell us? It tells us, you see, that basically I'm taking the point P, and what I'm doing is really I'm taking the exponential map at P, and I'm looking at its derivative along all okay, so maybe, yeah, let me say this. So here is so in the tangent space, this is say U, and this is U perp. Okay. And I know that by the Gauss lemma, the exponential map here, it will map the tangent space. It will map the U perp to gamma prime perp, right? So this is gamma prime, and this is gamma prime perp, right? The derivative of the exponential will map U perp to gamma prime perp, right? Yes?
Yes.
Yes, sir.
Right. Actually, what are the values of the derivative of the exponential? They are basically values of Jacobi fields, right? With initial conditions of the form J0 equal to 0, J prime 0 equal to V element of U perp, and then JT is basically the derivative of the exponential applied to V, right? Yes?
Right. Yes. Yes, sir. Yes. Yes.
Right? Okay.
Yes.
So, because what is JT? It is del del S at S equal to 0 of XP of TU plus TSV. Yes? Right? So by the
Right.
chain, this is the derivative of the exponential at TU applied to TV, right?
Yes, sir.
Okay.
Yes.
So so what does this tell you? This tells you that the norm of this is independent of V, right? It only depends on norm V rather. The norm only depends on norm V. So actually, like if I take the a unit sphere in this U perp, that goes to a sphere in gamma prime perp, right?
Yes. Yes.
Right. So if I take t equal to 1, then I get so if I take t equal to 1, do I want to take t equal to 1? 1 second. Well, what I'm trying to say is basically the following. That basically I can use the exponential. Oh, sorry, wrong. Okay, sorry. So, okay, let me just write this. So, norm JT, this is norm V sin HT, right? That's what we've seen. And this is equal to norm of dx p tu of TV, right? Okay.
Yes, sir.
Right. So
Hmm,
if I
right.
take so what is my so you see this norm, the norm of the derivative of the exponential, this only depends on norm v, right? So it's the same in all directions basically. So the
Hmm.
exponential stretches by the same amount in all directions. Okay, so the image of a sphere in u perp will be a sphere in gamma prime perp, right?
Hmm.
Okay, it stretches by the same amount in all directions. And now what I can do is I can use the exponential map to define polar coordinates on Hn. Okay, so what are my polar coordinates? Basically, I have a map. This is the polar coordinate map. Let's say phi. This goes from the unit tangent space at P, TP1 Hn. So this is a sphere, Sn minus 1, right? Cross 0 infinity. So u comma t this goes to x, sorry, Hn minus p. Okay, so this is your polar coordinates map. This is polar coordinates. Okay. This maps to xp of tu, right? This is a diffeomorphism. Yes.
Yes, there is a difference. Yes.
Okay, by the Cartan and Hadamard theorem, this will be a diffeomorphism.
Yes.
Is this clear? Utsav, is this all right? Yeah. This
Yes.
polar coordinate map, right? Okay, so this here, this is the sphere of radius t over here. Okay, and so what you can do is you can use this to write the metric of Hn in a different form in what's called the polar coordinate. You can write the metric in polar coordinates. So and this is often useful to do this. So what do I mean? What I mean is I pull back, so I have G tilde. Okay, this is a metric on TP1 Hn cross 0 infinity. Okay, so this I can identify with Sn minus 1 cross 0 infinity. Okay. G tilde is equal to phi upper star, the pullback of G, which is the metric on Hn. All right. Yes.
Yes.
Okay.
Yes.
Now, what will this metric look like? So let theta be the usual round metric Okay, so, okay, let me call it d theta squared. Okay, fine, it's a metric. So let me call it d theta squared. This is the usual round metric on Sn minus 1. Okay, of constant curvature plus 1, right? Okay, so if I take now, what will, so if I take a point, say U in T1, TP1 H1 and T in 0 infinity, okay, and I take a tangent vector to this, okay. So what will a tangent vector look like? So okay, let me give this a name. Let me call this okay, so we've got less than a minute. So let me stop here and then we'll start another meeting. Okay.